Julian, can you hear us?
Yes, I can hear you.
Yes. Are you ready?
Yes.
Yes. Go ahead, please.
Okay. Then, yeah. Thank you for turning begin. Yeah, for the second talk in this series. So where did I leave yesterday? I said I wanted to define equivalent relations for exact categories in some way, make sense of this notion, and yeah, maybe say a few words which exact categories can be described with this method. And yes, then I suggested this this notion for equivalent relations for an exact category. So it should be a pair of a basic subalgebra of some finite dimensional algebra, such that the big algebra is a projective generator over the small algebra. Then there's this, yeah, condition that the inclusion as viewed as a right module map has a left inverse whose kernel is a right ideal. You have this isomorphism condition on X groups of simple modules, and you want the exact category to be the category of induced modules. Yeah, and this is somehow based on joint work that started for me 10 years ago. And yeah, these are maybe some of the main papers that I wrote in this time. Okay, and the papers have this theorem somehow that such a description is possible for the category of filtered modules over a quasi-hereditary algebra. So the category F delta is equal to some category of induced modules from some subalgebra to the big algebra, and the subalgebra is basic, and yeah, the other conditions also hold. And the induced modules of the simples are the standard modules for the quasi-hereditary algebra. Okay, and then there's the uniqueness result. As I said in the first talk already, I state everything for quasi-hereditary algebras because that's the setting I'm very familiar with. I should note that there have been papers recently which have proved similar results in the setting of left or right standardly stratified algebras, which is a bit more general notion. Okay. Yeah, where you allow homomorphisms between the standard modules, for example, for the left standardly stratified case, let's say. Okay. Yeah, so the goal of this talk will be to go through the conditions and explain a bit the reasoning behind them, why they are there, what they're good for, why you couldn't be like, could you do a bit better? Could you ask, I don't know, R to be basic? Could you ask this isomorphism for more modules and so on, right? To explore with the conditions, see what they're good for and why you don't ask for anything stronger. Okay, and so I will go through the list somehow in order. Okay, so the first one is maybe the one that I have to justify the least. It's asking some subalgebra to be, or some algebra to be basic. Let me do it nevertheless. So you have this pair of a subalgebra, which is basic at the big algebra. And one way to look at a subalgebra of an algebra is as a monoid object in the category of bimodules. We'll see this viewpoint later on as well. And a subalgebra means, of course, that the unit morphism is then a monomorphism. Okay. Now assume you have another one, right? A pair A so a pair A comma R, where A is a subalgebra of R, and you have a Morita equivalence from A to B. Then, of course, it's well known that this induces a Morita equivalence of bimodules, right? And so you can transport R via this equivalence of categories to some monoid object in the category of BB bimodules, right? And so therefore you can somehow, yeah, go from one to the other. So even if A is not basic in the first place, you can choose pass to the basic representative. So that works fine. Yeah. And then you would have to check that the other conditions also yeah, get preserved if you pass via this. Okay, so that's maybe no harm here. Okay, but now, yeah, we have this pair A comma R. So you might ask, okay, A is basic, maybe R is basic as well, right? So that would be best case scenario. Is it not? And there was this, at least to me, surprising result by Teresa Conde last year. She proved in the quasi-hereditary case when this happens. So when you can choose R to be basic. So given all the conditions before that I asked as well, you have that R can be chosen to be basic if and only if the radical of all the standard modules is nabla filtered, has a filtration by co-standard modules. I didn't define these co-standard modules. They are some sort of objects which are dual to the standard modules. So yeah, there's certain highest weight submodules of the indecomposable injectives, if you want. And that's a very strong and very unusual condition, I would say. So in the examples of quasi-hereditary algebras, one is mostly interested in coming from Lie theory, like blocks of category O or Schur algebras. That condition is basically never satisfied. We'll see this in a moment. But it's sometimes satisfied. Also in the paper that Teresa wrote, and also in previous and later work, we found some examples of quasi-hereditary algebras where this condition, that the radical of the standard modules is nabla filtered, is satisfied. So for example, it's satisfied for quasi-hereditary algebras with at most 2 simple modules, or more general, if you have asked the essential order to be of height at most 2. Okay, yeah, these can be completely classified. They, yeah, basically enumerated by the number of arrows from 1 to 2 and from 2 to 1. So, yeah. It's earlier work. And then Teresa gave a nice example in her paper. I won't define this in detail, but it's you take the path algebra of a tree, and then what you do is you take what's called the dual extension algebra, which is a notion due to Chang Shi. What you do is you take the path algebra and you take the opposite algebra and you glue them together, and the relation you ask in addition is going in one direction and the other direction, right? Going is always 0. And then you take the Ringel dual of these algebras, and these algebras form a class of algebras where this condition is always satisfied. Okay. And then recently, my PhD student has studied path algebras of linearly oriented AN quivers. So these are hereditary algebras, and the theory of quasi-hereditary algebras says that hereditary algebras are quasi-hereditary with respect to any order you can put on the simple modules. And what he proved, based on this previous work by Flores, Kimura, and Rognaru, is that also this condition, the radical of delta is nabla filtered, is satisfied for path algebras of linear and AN quivers. Okay.
Hello, I think I'm not
Yes.
understanding something. If the radical is filtered, then the top is also filtered, isn't it? Because the projectives are filtered.
The radical of the standard modules is nabla filtered. Should I do an example, or what? The top is just a simple, and that's not nabla filtered, right? Simple modules are usually not nabla filtered.
Yes, but now if the radical is filtered, I don't understand. If the delta is filtered, delta I, because it's one of the
delta I, no, sorry, nabla filtered. So delta I, of course, delta I is delta filtered, but I'm asking for nabla filtrations.
And nabla are the co-standard modules, right?
The co-standard modules, yeah. So the nablas are the co-standard modules. So the radical of the standard modules should be co-standard filtered.
Okay, sorry, I know what I did. I thought wrong. Okay, thank you.
But it's a very rare condition, so it's a yeah. It's quite kind of strange. Yeah. But, yes. She also gives several other conditions. One of them is that the delta i's are actually the approximations of the simple modules with respect to the delta filtered category. Okay. Yes. So let me continue. So if you look at this last theorem here, or this collection of theorems, so this theorem is wrong if you somehow go a bit further or a bit different from these classes that I list, right? So if you take a quasi-hereditary of algebra with 3 simples, it's usually doesn't satisfy this condition. If you take, instead of the ring dual, you take the dual extension of the path algebra, that's not doesn't have a basic R. If you take any other orientation of an n quiver or some dn quiver, it's usually not true. So yeah, so it's a rare condition. Okay. Yes, so if it's not basic, the multiplicities might say something. And in the same paper, Teresa gave actually a recursive formula for the multiplicities of the projectives in R. So here's the formula in all its glory. Yeah, you can compute with it. Maybe the most interesting feature is that it's a really explicit formula. It has an input just some sort of the composition multiplicities of the simples and the standards, the simples and the co-standards, and the dimension of the Hom spaces between the standard modules. Okay. And in particular, the R is unique. That's a consequence here, right? But if you compare it to the uniqueness that I mentioned earlier in this theorem, Teresa's statement only applies the uniqueness of R, whereas this theorem here implies the uniqueness of the tuple AR. So A is a subalgebra of R. Okay. Yes, so because I realize I have some time, maybe with 3 talks, I thought maybe I'll try to use this theorem and give you some examples, and let's try to choose some real-life examples. So you can take Schur algebras of symmetric groups, and yeah, let's take some representation finite block of a Schur algebra, and with 2 simples, we saw it's basic. You will need a basic algebra. So let's take one with 3 simples, and luckily the equivalent relations have been computed in this case. So it's this path algebra of this quiver with these 2 relations. Okay, and then if you apply this theorem, you will get that the multiplicity of the first projective is 1, of the second projective it's 1, and of the third projective you have to work a bit. But actually all these numbers that you have to put in here are actually 1. So it's 1 plus 3 times 1 minus 2 times 1. So that's 2. Right? So here you see an example, quite an easy one, of a quasi-hereditary algebra where this R that you get as an output will actually be not basic. And yeah, if you can, this is part of a family with n simples, and at some point I computed what you get in general for arbitrary n, and yeah, in general this will be a family of algebras with n simples and dimension 4n minus 3, and if you look at the R, it has dimension, which is a cube in n, right? So a cubical polynomial in n. So yeah, it's quite far from being basic. Okay, and for another example, yes, I'll write this out again. Another example. Sorry. Yes, I forgot this. I mentioned this as well. So Angela Klamt and Katharina Stroppe proved in 2012 that actually the X algebra of the deltas doesn't have higher multiplication. So you only have to deal with the M2 here. Okay. Yes. And then I looked at another example of Katharina Stroppe. I think that comes from her PhD thesis in 2003. And it's the principal block of SL3. It has this funny looking quiver and a bunch of relations that I won't want to write down here because it's a pretty long list. You can look at the paper if you are interested. And yeah, again, all the multiplicities and home spaces are one-dimensional. And yeah, I did some computation today in the morning, and this is the result I got. So multiplicities of the first layer here, 1, 2, and 3, first and second layer, I should say, is 1. And then this third layer of consisting of the modules 4 and 5 appears with multiplicity 3. And then the last one with multiplicity is 8. So in other words, the R that you obtain actually is the endomorphism ring of P1, P2, P3 all once, and then P4 and P5 3 times, and P6 8 times. And as far as I'm aware, in this case, the A-infinity structure on X delta delta has not been computed. So yeah, I actually don't know whether it has any higher multiplication or not. Okay. So that was the first condition, exploring whether why A is basic, or why you can ask A to be basic, but why you shouldn't probably ask R to be basic. Okay. Now I'm going to the next condition, and one crucial feature here is dualizing algebras or rings. And yeah, this is something that's somehow hidden in the background that I've not talked about so far. I've tried to keep all the co-structures out of the picture for now, but now they will appear more and more in this talk. Yeah, so oftentimes it's quite convenient to switch from algebras to it gets sometimes rid of certain finiteness conditions somehow. But yeah, it's maybe less familiar to people, but it's actually oftentimes quite convenient. And yeah, for example, I have this nice lemma, right? That if you take a co-algebra and you take the dual, you will arrive at an algebra. But the converse is not true. So if you take the dual of an algebra, you will in general not get a co-algebra. But you have to ask your algebra to be finite dimensional in general, then it will work. Then you will get a co-algebra. Okay, but I've talked before about this monoid objects and comonoid objects. So let me give this definition more explicitly. So what is a monoid object in the category of bimodules? And that sometimes comes, the notion is called an A ring sometimes in the literature. So what is that? It's a monoid object. Should have a multiplication in the unit. So the multiplication I denote by M. So it's a bimodule map from R tensored over A with R to R. And then you need a unit map, eta from A to R. And they should satisfy the standard associativity and unitality axioms that you can write down quite easily. And of course, there's a dual object called an A co-ring, where instead you have a map, which I would like to call mu, coming from this literature of boxes. So some map mu from my co-rings are usually called V, so V to V tensor V, and some epsilon from V to A. Right, and they should satisfy the standard co-associativity and co-unitality axioms where you reverse all the areas. Okay, And then already Sweetler in 1975 observed that this little lemma that you have here generalizes somehow to the setup. So the A dual of a co-ring is a ring, but the converse is of course not true, but it's true if you asked your ring to be finitely generated projective on the side where you're dualizing now. So if you're dualizing on the right, then the right dual will be co-ring. Okay. Yes, that's something I did hide here. So actually there are two duals. You can take the right dual and the left dual, right? Because the action of A is not central, but doesn't even make sense because A is not commutative. So you can take two duals. You can take a right dual and the left dual. And you have to ask for finally generatedness on the side where you dualize. Okay. And then I don't know whether this was known before, but we didn't see it in the literature. In this joint work with Tomasz Brzezinski and Steffen Koenig, we observed actually that that the notion that R as a right module being a projective generator, not just finally generated projective, but a projective generator is actually quite an important condition because it grants us that the co-unit is a surjective map, which is also in general not true if you're dealing with co-rings. So the co-unit, if you're going from co-algebras over field to co-rings over an associative algebra, it does not need to be surjective in general. But in the setup I'm working with, it will be surjective, and this is guaranteed by this condition that R is a projective generator on the right. Okay. Yes, so that was the second condition. That's as much as I can tell about the second condition. Okay. The third condition was this condition that the inclusion of the subalgebra into the big algebra as a right module map has a left inverses kernel is a right ideal of the big algebra. This is actually some condition that was observed by Mark Kleiner in 1984. He proved that this condition is actually equivalent to some condition on the co-ring. So on this dual A co-ring, taking dual on the right, from R, A, this is has a structure of a co-ring with co-multiplication being the dual of the multiplication and co-unit being the dual of the unit. And the condition is that there exists a group-like element. So what's a group-like element? So if you think about the group algebra of a finite group, the group algebra is a Hopf algebra, so there's a co-multiplication, and the co-multiplication of the group elements is as follows. Let's call this delta for now for the co-multiplication of the group algebra. Delta of G is G tensor G, and epsilon of G is 1. And such an element in general is called a group-like element. So that comes from this setup. And this also makes sense for co-rings over associative algebras instead of co-rings over fields. And these need not exist, but if they exist, then the co-ring is called normal, and then somehow it's dual to this funny-looking condition of the inclusion. Yeah, I don't know whether this is convincing, but let me go one step further and say, what can you do with such a group-like element? And for that, let me go back to the first ICRA, where Kleiner and Roiter wrote some proceedings article in 1974. And this proceedings article was actually about what they call semi-free differential graded algebras. I mentioned this in the abstract of my series of talks. So what is a semi-free differential graded algebra? It's some graded algebra which is equivalent to a tensor algebra. So TA of V bar for some AA bimodule V bar, equipped with a differential. And because it's a tensor algebra, the differential is actually determined by what it does in degree 0, and in which is algebra A, and in degree 1, which is this bimodule V bar. So that's what Kleiner and Roiter wrote in their 1974 proceedings article. And then, yeah, based on that, Roiter in 1980 related this to the notion of a co-ring, or he called it a box at the time, for bimodule over category with co-algebra structure, being a bit more general, somehow replacing the algebra A by actually a category. But this is somehow, yeah, a distinction that I don't want to go into so much. Yes, but back to this theorem here, enough of history. So this theorem deals more generally with the situation. So if you have a co-ring V and the co-unit is surjective, so in particular you have some omega which is sent to 1 via the co-unit. Yeah, then you can actually cook up a semi-free differential graded algebra as follows. So what you do is you put your algebra A that you're working over in degree 0. Then you put the kernel of the co-unit in degree 1, and you build this tensor algebra. And then you can define a differential on it. How do you do that? In degree 0, the differential is somehow the commutator of your element A that you put in with the chosen base point omega. And in degree 1, it's somehow the difference of V in some sense being primitive, one could say. So D1 of V is omega tensor V plus V tensor omega, yeah, minus mu of V. So yeah. Okay. Yes. So I said this is differential. And this would actually be true if omega is a group-like element. So that was what Roiter discussed in his article in 1980. But it holds true more generally. You just don't end up with a differential graded algebra, but with what one calls a curved differential graded algebra. So you have this curvature term gamma, which is the difference somehow of omega being group-like. So it measures how far omega is from being group-like. So it's omega tensor omega minus mu of omega. Yeah. Yes, I have a short slide telling you what a curved differential graded algebra is, but I will never use it in the future. It will just not. This theorem is just there to justify why one would want normality of this co-ring. It's actually a nice condition because then some associated curved DG algebra is actually a DG algebra. Yes, so curved DG algebra is a graded algebra with this differential that satisfies the Leibniz rule, but d squared of some element is not 0, but it's actually the commutator with the curvature term, whose differential is 0. Okay, so yeah, that's why one would want this condition on the embedding having a certain splitting as a right module map. Okay, now that's maybe the crucial condition, this isomorphism of X groups, and the one that didn't show up before so much. Yes, So you have this condition of an isomorphism of X groups for all I greater equal than 1, from the simples of the subalgebra to the induced modules of the simples of the big algebra. Okay, you might ask why I only asked for simples and not for all modules. Actually, it's almost true for all modules. It implies that it's true for all modules. It's an isomorphism for I greater equal than 2. But for I equals 1, you have some problems because somehow the HOM interacts weirdly, if you want. The HOM in the HOM setting, it doesn't work. So yes. Okay, but what's this condition? This condition is also very nice. In this paper, we call it a homological subalgebra. And in fact, if you're working over a perfect field, which most of us are doing, I suppose, then this condition is actually equivalent to the fact that the kernel of the co-unit for the dual co-ring is a projective bimodule. And yeah, so you see this somehow maybe funny looking condition on the algebra side translates into some completely natural condition on the co-ring side. And that's actually how we discovered these conditions somehow. And somehow on the co-ring side they seem natural, so we looked what do they translate to on the algebra side and obtained some condition. That was maybe looking a bit less natural, but nevertheless turned out to be very useful. Okay. And yeah, here's another corollary. And this is where this condition was discussed extensively, this condition of being an epimorphism, this map of X groups, right, being epimorphism in degree 1 and isomorphism for higher degree. This was discussed by Burt and Butler in 1990 in the proceedings of the 5th ICRA in Tsukuba. And this, in particular, this condition implies that the category of induced modules is actually an exact category, so it's closed under extensions. And furthermore, if you assume it's idempotent split, then that's resolving. So satisfies all this nice conditions. Of course, it contains projectives, but if you assume that it's idempotent split, it also closes on the kernels of epimorphisms. And also it has enough injectives, and the injectives are given by the additive closure of the dual of the dual co-ring. So this is just the K dual of this thing here. Okay. Yeah, and it's actually worth reading the results that Burt and Butler have for co-rings. That's, I think, a nice homological introduction to the theory of co-rings, if you want to learn more about this. Okay, so why not ask for more? This was some question that I was asked last year, and yeah, we have this somehow discrepancy between degree 1, where you ask for an epimorphism, and degree greater or equal than 2, where you ask for an isomorphism. And actually, as part of some joint work, if you ask this to be an isomorphism for all I greater or equal than 1, then actually this means that the inclusion here of A into R splits as a map of bimodules. And yeah, I wanted to tell you that because my master students then discovered that this is actually some condition that is mentioned in the book by Brzezinski and Wiesbauer on co-rings and co-modules. There is some homological condition that detects this. It's the vanishing of the first Hochschild cohomology, so co-ring Hochschild cohomology for this dual co-ring. And yeah, one can work a bit more and see that in this quasi-hereditary case, this is somehow is a special case of the of the case when R is basic, so the radical of the delta is Nabla filtered. So it's quite rare. So you shouldn't ask for this condition because it's even more special than R being basic. Okay, but yeah, it maybe opens the door. Maybe one should look more into for different cohomology theories for this co-rings or relative Hochschild cohomology also for this. I think this would be worth exploring more what happens here in this setup and more generally for these kinds of subalgebras. Okay, let me go on, go further. And now that I discussed a bit all these properties that you ask for, that I asked for A and R, it's maybe good to go to the question: how do you get actually A and R? Yeah, can you construct them if you didn't know them beforehand, right? If you just start with an algebra lambda and you want somehow some algebra R Morita equivalent to it that has a nice subalgebra A, and actually it goes as follows. So this is a theorem in this joint paper with Vanessa Miemietz from last year. Actually, this theorem is somehow maybe the starting point of our joint project. This was the first result we obtained quite some years back. And it says that if you look at the A infinity structure on the X algebra of the simples, and you compare it to the A infinity structure on the X algebra of the induced simples, then you get an isomorphism for A infinity algebras. Yes. So we have been asking for this isomorphism. So these things should be isomorphic as vector spaces. That was one of the conditions. But it's actually not just an isomorphism of vector spaces. You can actually view it as an isomorphism of A infinity algebras. That's the content of the theorem. Okay. So what does that mean? That means if you want to realize, if you want to compute A and R, you can compute A. What you have to know is you have to know the A infinity structure on the things that you want to be the induced modules of the simples. Yeah. So, and this you do then by via Keller's construction. Yeah. So you take this, take these MNs from a bunch of X1s to X2, and then you take the tensor algebra of the dual of X1s and mod out by the image of the dual map, which goes from X2 to the sum of the tensor powers of X1s, the duals. Yeah. Okay, and yeah, that's actually how this was constructed then in the first paper, right, with Steffen Koenig and Sergiy Ovsienko. Okay, so what's the slogan? That's not maybe precise yet, but I think yeah, several people have been working on this a bit. In some sense, what happens here is that mod A, the module category of the subalgebra, is some sort of abelian approximation of this exact category of induced modules inside R, right? So if you look at this, right, what is it telling you? It tells you that somehow the space of extensions, even as an infinity algebra, coincides in the positive part. Sorry. And the only thing that's somehow different between these two things is the interaction with the degree 0 part. So how the homomorphisms are put into the picture. Yes. So in some sense, mod A is the answer to the question that's maybe sounds a bit crazy. if you take this exact category of modules filtered by certain R tensor Li, and you remove all the maps that don't come from identities on the composition factors, right? What abelian category do you get? Yeah. Okay. So that's what A measures somehow. Okay. So now this tells you how to construct A. So in particular, it tells you that also A is unique. This is a proof from this. So we have uniqueness of R from, for example, Teresa's result, which doesn't use any A infinity structure at all. And you have uniqueness of A from this, I think, quite basic result if you know the theory of A infinity algebras. But a priori, these two theorems are not connected. So it's not clear that the isomorphisms, the two isomorphisms are compatible in any way. And that's, yeah, what I want to talk about next, and also how to put in these radical maps, these other homomorphisms, the non-identity homomorphisms. Okay. Right. So what's the meaning of these maps, of these radical maps between the modules in question? So in the quasi-hereditary case, the standard modules. So let me recall how we did things yesterday. We thought said the important maps in the case of the X algebra of the simples are the maps MNs, which go from the tensor product of X1s to X2. Now we have this theorem in the background with Vanessa that says, actually, if you're looking at X1s for the subalgebra between the simples, you can also look at the things that should be the induced modules, which in the quasi-hereditary case are the standard modules. So look at the MNs, which go from a tensor product of X1s between the standard modules to the second X between the standard modules. Okay, so these are the things that give you your subalgebra. But actually there are more. If the delta I are not simple, which they are normally not, right? Then there are further important maps, actually. You also have to see how they interact with the HOMs. And there are two families of maps. One is you take a bunch of X1s and you put in one copy of HOM, so some radical map. And then another bunch of X1s. And if you count, right, you have almost all of them are X1s except for one. So this is somehow the degree of these are n minus 1. And the total degree. So, and mn has degree 2 minus n. So 2 minus n plus n minus 1 is 1. So you land in X1 between the deltas. And then there's another bunch of maps which allow you to have two copies of the radical, right? Okay. And this is all you can do just using HOMs and X1s. Okay, because otherwise you land in, for degree reasons, right? The result would be in negative degree, and the X algebra has no negative degree. Okay. Are there any questions about that? Otherwise, let me know. Yeah. Okay. And the idea is somehow you can use these maps to construct the R. Yeah. Okay. And how do you construct the R? So at first there are 3 reduction steps. So the first one is, if you want to construct the R, you can as well construct the dual covering, because everything is finally generated in projective. So dualizing and dualizing again, right? You'll get it back. So if you want to construct R, instead you can construct this A covering V, because then you can get the R as the dual. Okay. And then there's this Roiter equivalence. I didn't say this before, but this association of a covering to this semi-free DG algebra is actually an equivalence of categories. So to construct the V, you can also construct the semi-free DG algebra TA of V bar. Yes, so that's the second reduction step. And the third reduction step, yeah, you have the semi-free DG algebra, this I mentioned before. A semi-free DG algebra is determined by the A, the V bar, and the two maps, D0 going from A to V bar, and D1 going from V bar to V bar tensor V bar. Okay, and then there's a, yeah, this is part of the third reduction step, and the third reduction step actually says, okay, you can do this on generators, right? Because the D satisfies the graded Leibniz rule. Yeah, it suffices to define D0 and D1 on generators. Okay. Great. So yeah, now we have to know what is A, what is V bar, and what is D0 and what is D1. A, I already said, it's somehow the thing you get when you apply this A infinity Gaussian duality to this maps MNs from X1 to X2, right? So what about the other information that you do here? And for this other information, we have to compare maps. So I said what's important is this other N here, which has as input a bunch of X1s and one hom component, and going to X1. And this map actually is related to the map D0 in the semi-free DG algebra, which goes from A to V bar. How is it related? So actually, V bar is a projective bimodule that we saw before, right? V bar is the kernel of the co-unit of the dual covering, which we wanted to be a projective bimodule. This was one of the conditions that followed from this isomorphism condition on X groups. And actually, one can prove that V bar is a projective bimodule with generators given by a basis of this dual of the radical, or the dual of the space of radical maps from delta to delta. Okay. And so now if you compare the two things, right, on the left-hand side, you have this A, which is generated by the dual of X1s. And on the right-hand side, you have some projective bimodule, which is generated by the duals of the radicals. I'm saying to you, then these two things actually look quite the same. In fact, they look dual to each other. So if you start with the MNs, right, then you can dualize, then you get a map from the dual of X1 to some dual of X1 to some power, tensored the dual of the some hom space, tensored with a dual of some power of X1. Okay. Yes, actually, so the MN hash will, of course, go to the sum of all these, right? Summing over all J and K, which add up to n-1. But okay, if you do all the summing and then you project also this thing here, modeling out some of this image of the dual of the MNs, so that you get A here and A here, what you will get here is A tensor the dual of the radical maps tensor A. So this will be V bar. So what you actually get is a map from the dual of x1 to V bar. And the dual of x1, I told you, were just the arrows of this path algebra, of this bound path algebra A. So you get a map, the restriction of D0 to the generators. So some map from the dual of x1 to V bar. So given the infinity structure on x1s, we are able to get the D0. Okay, and similarly, this works for the second map, the map in degree 1, this D1. So here you look at the other MNs, so the MNs which have 2 Hom inputs and otherwise X1s. Again, the V bar is a projective bimodule generated by the dual of the radical, delta delta. And then if you have the MN, you can dualize it. You get this kind of map. And then you can sum, and then you get some map from the dual of the radical to, if you project to the tensor product of V bar with V bar, right? So if you write this out, V bar is isomorphic to A tensor, the dual of the radical tensor A. And if you tensor 2 of them together, you get A tensor dual of the radical tensor A tensor dual of the radical tensor A. Okay. So this is how D0, D1, A, and V bar are constructed if you know the A infinity structure on the X algebra of the standard modules. Okay, and you need precisely the 3 inputs, somehow the X1s with only, the MNs with only X1 inputs, the MNs with 1 Hom input and otherwise X1s, and the MNs with 2 Hom inputs and otherwise X1s. Okay. Now, if you remember what I talked about yesterday, one of the slides was somehow going the other way around. So mentioning that if you have a presentation of the algebra as by a quiver and relations, then you can construct an infinity structure on the X algebra of the simples. And somehow this is a big part of the theorem with Vanessa Miemietz that we published, we put on the archive last year. It's actually the analog of this result for the setup of the X algebra of the standard modules. To give you the idea. So if you have this basic A given by a quiver with relations, so KQ mod I, and you have this regularity condition that the X algebra of the simples is the X algebra of the induced simples, which are the standard modules in this case, then you have the following bunch of isomorphisms. So yeah, the arrows of the algebra, they are given by the dual of x1. The generators of the admissible ideal, they're given by x2s between the standard modules, and the radical maps between the deltas, they're given by this bimodule top of the bimodule V bar, which is the kernel of the co-unit of the dual co-ring of this R. Okay, and then the idea is that if you, similarly to what Keller did, if you choose some splitting of the projection of I to I modulo Q plus IQ plus, giving you some map from this X2 space, from this space isomorphic to X2, to the tensor algebra of X1s. And yeah, furthermore, you choose a splitting of the projection of KQ to KQ mod I, and you choose an isomorphism of V bar, realizing it as a projective bimodule. And if you choose all these splittings slightly in a compatible way, so there's some restrictions on that, and you dualize this, then you get these maps MNs, so we're going conversely to what we did on the previous slides. And you get these MNs, and the theorem that's behind the unique result is actually things are part of the model, the extent of the sum of models. Okay. Yes. And yeah, and maybe to finish off for today, so the idea of the uniqueness result is then to say, okay, if you have two different presentations, you can use both presentations to cook up A-infinity structures on the X algebra of the standard modules. And then Kadishvili's result will tell you that these are isomorphic. And then, okay, they are isomorphic, so then you can go back, you can get presentations of A and R, so to say. And these somehow are inverse to each other, these two constructions. So if you start with a presentation, you define an A-infinity structure, and then you go back and get a presentation, then this presentation will be the same. So that's what's happening here. And so the uniqueness of the Kadishvili result then tells you that if you dualize again, you will get isomorphic A and R. Yes, and that's all for today. And on Saturday, I will talk a bit more about somehow how this feels then like quiver representation theory. And I will also talk a bit more about the methods behind this uniqueness result and how it's proven a bit more detail. Thank you for today.
Thank you very much, Julian. Are there any questions?
Okay, I see a comment by Doug saying that the higher products vanish in the SR3 example. If you have a reference for that, I would be very interested, or some computation. Yeah.
Hi, Julian. So can you give more information on what is phi here? So in this isomorphism.
Okay. Yeah, phi. So we're working over an algebraically closed field. So projective bimodules are always of the form AEJ tensor EIA. And somehow this phi collects the generators. So so it's somehow A tensor over L, phi tensor over L, A, where L is this product of fields. So it's just one way to collect this information, this projective bimodule, projective LL bimodule.
Okay, thanks.
Any more questions? If not, let's thank Julian again.
Thank you.